Buongiorno a tutti e grazie per la vostra partecipazione a questo webinar. Webinar dal titolo Dalle benzine ai greggi, applicazione della distillazione simulata per via gas cromatografica. Con me vedete Fabrizio Ghisolfi, che è il nostro senior specialist di queste linee applicative, e abbiamo due ospiti, Theo Boekee, che è il PSC Application Support Manager, e Arjan Zijp, che è Regional Sales Manager del Analytical Controls, oggi parte del gruppo PAC, e sono collegati con noi dall'Olanda. Abbiamo, come vedete appunto nell'elenco degli speaker, Analytical Controls è il nostro partner fin dai primi anni 2000 nel posizionamento degli analizzatori per applicazioni nel settore petrolchimico, raffinerie, oil and gas, per i laboratori chimici che utilizzano questo tipo di che svolgono questo tipo di applicazioni. Vi ricordo alcuni analizzatori prodotti e estremamente diffusi in Italia, quali Reformulizer, quali gli ISP RGA per gli accreditamenti ISO 15984, oppure gli analizzatori in tracce di ossigenati in idrocarburi piuttosto che di solforati, e infatti abbiamo fatto proprio un anno fa un webinar sul rivelatore Sense SCD per la determinazione di tracce di solforati in matrici idrocarburiche, e che se volete potete rivedere attraverso il nostro sito web. Questa volta abbiamo scelto un argomento che è appunto la distillazione simulata, quindi la determinazione della distribuzione dei punti di ebollizione nelle miscele di idrocarburi. È un'applicazione anche questa estremamente diffusa, molto ampia, nel senso che è applicata sia a prodotti leggeri, quindi parliamo di benzine, parliamo di nafte, fino a prodotti pesanti, pensiamo ai residui, ma addirittura ai greggi, quindi con una range di punti di ebollizione anche estremamente ampia, come può essere appunto un greggio. In questo webinar, grazie anche alla partecipazione dei nostri partner di PAC, faremo una bella carrellata sulle applicazioni, ma ci teniamo anche a darvi delle nozioni teoriche sulla tecnica e delle informazioni anche sulla tecnologia oggi impiegata per coprire queste applicazioni e sui nuovi software che sono anche compatibili con i nuovi metodi, quindi i gruppi di lavoro sono sempre molto attivi, quindi nuovi aggiornamenti ci sono stati in questi ultimi mesi o ci saranno, e quindi i software sono adeguati a queste nuove metodiche. Il webinar sarà in lingua inglese, però come molti di voi sanno, l'inglese dei colleghi è un inglese olandese molto comprensibile, molto light, e quindi credo non ci siano problemi. Comunque sia io che Fabrizio poi al termine del webinar saremo presenti per poi domande e darvi eventualmente dei chiarimenti su alcuni aspetti. So I want to first of all thanks to Theo and Arjan for your participation to join us this morning for the webinar. I know you will introduce yourself in your presentation, so I can give to you the lead now, Theo and Arjan, and you can share the presentation and you can start the webinar. Thank you.
Well, thank you, Gianluca and Fabrizio, and thank you and welcome you all to joining this session of the AC SIMDIS introduction and presentation. Let me introduce ourselves a little bit in the following slide, and as well to show you a little bit the agenda, what we want to discuss.
Can Gianluca confirm that the screen is visible?
Yes.
Okay.
Yes.
Yes.
Thank you.
Okay. So if we can go to the next slide, I will tell you a little bit about the agenda, what we're going to do. First, we're going to introduce ourselves in the following slides. And then Theo will take over talking about distillation, and you can see quite a big list of topics that we want to cover. So we're talking about general distillation, what is SIMDIS. Of course, we're going to compare SIMDIS to the actual physical distillation, which is an interesting topic. Talk a little bit about what is the AC SIMDIS hardware, what is the difference and where is our strength, the correlation, SIMDIS, high temp and crude analysis, and we're going to show you a little bit a demo of our software as well. So stay tuned during this session, and if you've got questions, feel free to use the chat or intervene or raise your hand if you have something. So let's start with myself first. So my name is Arjan van Zijp. I'm the regional sales manager and customer service manager for AC Analytical Control and PAC. I'm now in the business of sales already since 2001, and I'm working for several companies like Shimatsu, Bruker, PSC in the past for process, Neste as an refining company, and now since the last 4 years already back with the PSC for with the responsibility of the GCs and elemental business. Of course, my dear valued colleague next to me, Theo Boekee, he has got a very long career timeline already, starting to work in 1983, but already almost from the beginning, 1992, till now at PSC in different roles. So this is my valued colleague where we definitely lean on. He's very much experiences in all the applications, and therefore now, when he moved from support manager as well from the sales manager, he's now in the new role as application support manager, helping me, of course, Gianluca and his team, SRA, but also you with all the applications that can help you drive your business. A little bit about PSC and AC. So AC is now already 41 years in existence. We have a new facility in Rotterdam now since 3 years. You can see a very nice picture here on the side. And we are very much, of course, starting to be and we started to do the applications on the pioneer on innovative chromatography. And you probably will know it's the reformalizer there where we started the business 41 years ago. We have set the market and target as well for the high-speed RGA, the high temperature SIMDIS, and the DHA front end. Of course, we have much more applications to cover and a lot of custom applications. And if you want to have a little bit more information about this, or you have questions, please feel free to contact us or connect to Gianluca and Fabrizio, and they can help you with that. I think the main message is, and that's something that we are carrying out through all our presentation as well as our way of working, is that we really feel that we deliver through turnkey solutions and an application warranty, because chromatography is a separation technology, but it's not an easy one. You need to have the special support for it, and that's something what we offer from the start. So it's not only about hardware, it's about the applications that you need to be doing. So that's really the message in orange as well, that we take care of your configuration and validation and making sure the user can utilize. You can utilize it from the start. I think this message will continue to go on through the presentation as well, Theo. And I think it will come back more and more, but that is really true. So if there's an issue with one of the instruments you have and it's based on application, it's us to solve it, and we make sure that you have the perfect solution in-house. And I think for now, this I will stop doing my introduction, and Theo will talk about the actual topic, distillation.
Distillation.
Theo.
Yes, thank you, Arjan, for the introduction, and same for Gianluca, of course. Topic of today is distillation, and we will focus on simulated distillation, but before that, a introduction on why and how it compares, etc. So looking in our industry, which we call the HPI, hydrocarbon processing industry, distillation is the most common used process. It's the let's say it's process number one in the refineries. And the reason for it is there are various. It's of course separating the crude oil into different fractions, and not only crude oil but also other products. It is so the boiling point information by itself is used for indeed predicting what can you get from your crude. For quality control, there are some rules, some compliancy to fit with, and of course to control the process. And talking about that, controlling the process, here you see a diagram of a refinery. You know better than I that refineries are not all the same, but this is just an example showing many of the processes that can be around. And the green dots represent where distillation, where boiling point distribution information may be important to know or can be of use for further information. And if you look to PAC, that is not only AC Analytical Controls doing the chromatography solutions, but we also offer online instrumentation and physical property testing information. So we have all kind of distillation technologies in-house, meeting your requirements, meeting your needs. This session will be about simulated distillation. Well, if we go back to the crude oil distillation, and this might be a bit of a complex slide, but basically what it shows that if you have the boiling point distribution of a crude, refinery distills it in further fractions, and each fraction has its own value, its own price. And of course, we all like to maximize the margin, so you like to produce as much of the most valuable products, thereby stretching it up to its limits. And to do that, you need to know how much you can get from such a product from your distillation. Well, here the example where the crude is separated in the naphthas, the kerosene, the mid-distillates, the VGOs, and what's left is of course the residue, and each having its own price. To predict, and that's this example where we show a boiling point distribution of a crude oil, and often the 90% point is of big value, and the small difference, and I'm not going in the details of the numbers, but a 1 degree optimization can impact this point, for example, 2.7 volume percent in this typical example, which has a value and a huge impact on a yearly basis by increasing the range or optimizing the range, and thereby earning money. Well, what does SIMDIS has to do with this? If you are able to analyze in a very accurate way, you're able to tune your process in a more accurate and a more profitable way. And if we look to just an example of results from our SIMDISes, and what you see here is on the left hand the graph where the red line represents from one of the typical methods, ASTM 2887 for mid-distillates, represents the reproducibility, and the blue line, the blue dots, represent the results from a round robin that we have organized already 10 years ago, where over 60 customers using our AC SIMDIS participated. And the data from that round robin is shown here in the blue line. And that means that we can prove that our installed base is capable of analyzing far within the method reproducibility. And that is, of course, not only reproducibility, also repeatability, which is then of a great use for you in optimizing your process and defining the product specification. The graph left, the table right are the same numbers. Yeah, so you can see on every point we are performing, our installed base, so to say, are performing better than what the method is demanding. So far about, let's say, the economics. I already mentioned as PAC that we have a wide range of distillation products. If we look to SIMDIS, and I'm going to explain later on what SIMDIS means, we have what we call regular SIMDISes for different type of products, the gasoline, the mid distillates, the high temperature for heavier products. We have in our software the ability to correlate results from our SIMDIS or DHA to D86 boiling point distribution. That's the correlations as listed here. We have a dedicated configuration where we use high temperature SIMDIS in combination with a DHA front end for detailed and accurate boiling point distribution of crude oil. And last but not least is what we call our CNS SIMDIS, where we do boiling point distribution not only for the product itself, so carbon, but also for the nitrogen and sulfur that may be present in those products, which is of course of great use later on to figure out where is the sulfur in my product and what does that mean for desulfurization, etc., and product spec. We are limited in our time, so I will not talk more about the CNS, but should there be an interest, then we can schedule a separate session for that.
Yeah.
Okay. Let's get into, let's say, more technical. What is SIMDIS? SIMDIS, people call it SIMDIS, or the full name is simulated distillation. And basically what we do is we determine the boiling point distribution of a product by using gas chromatography. And that's a basic concept where we assume that a sample, a product introduced on a column is eluting in its boiling point order. Well, that's shown here in a bit more detail. So from left to right, we introduce our sample through a inlet, and we use a dedicated inlet for that. We call it the TPI, temperature programmable inlet, for a gradient introduction of the sample into the TC column. There is no splitting, there's no venting whatsoever. So basically you can say, depending on the type of SIMDIS, what you introduce goes into the column. No discrimination over here. More about that later. Separation is taking place on a non-polar metal silicon column, programmed in a linear rate, so the sample elutes in its increasing boiling point number. What comes out of the column is detected by an FID, which is a mass-dependent detector. So you get a graph, which we will show you. And from that graph, we calculate the boiling point distribution based on a calibration analysis. And if I go to the next slide, then you'll see this explained more graphically, where right bottom over here, you see a typical diesel chromatogram graphically represented like this, like the triangle over here, where this is the retention time from left to right, and that's the signal. So if we take the total area and we assume this to be 100%, then you can cut it in certain fractions and then calculate 1, 2, 3, 4, 5%, and that elutes at a certain retention time. And based on an analysis of a mixture of normal paraffins with the known carbon, with the known boiling points, we know the retention time relationship to the boiling point. That's the calibration curve, as you see here. So then we have percentage related to a boiling point. And that is, at the end, the results you get from a distillation. Mass percent versus a boiling point. So typical diesel chromatogram, in this case with fame, as you can see here, and in the graph, in the chromatogram, you see the red line, which represents the boiling point curve graphically, and here in the table on the right hand, mass versus boiling point. Here we have taken 10% steps. You can take 1 or 2 or 5 or 20, whatever you like. If you know this, you can convert it as well from boiling point to mass. It's just the other way around. If you have an interesting boiling point to report, for example, 340, you can say, well, 80.7% elutes at 340 degrees C. And from there, you can also calculate your fractions from one boiling point to another. Just as an example of a regular diesel available. There are a lot more products to be analyzed on SIMDIS. I showed you the refinery diagram. Here some typical chromatograms from all kinds of products analyzed on the SIMDIS. So from the gasoline, jet fuel, diesel, up to heavier products like vacuum distillate, or even crude oil, FCC feed, and even residual samples. Small remark about the residual samples. They do not elute for 100%, and we calculate the results accordingly. We'll come to that later. So it covers the whole range of products being present in a refinery. That can not all be done on the same device. Well, having said that, yes, it can, but there is a difference in that. Before going there, here the standardization applicable for SIMDIS. A lot of methods from ASTM, EN, DIN, IP, etc., covering a full range of products from gasoline to crude oil, including the residual fuels, all with their own initial boiling point and final boiling point. Typically in Europe, used is this one for the jet and the diesel, and for example, where is it number 3 for the crude oil, which we'll talk about later. The differences between all those methods. Let's first say not the differences, but the similarities. The similarities is the technique. Sample is introduced through a direct injector, the TPI, going into the column, eluting in boiling point order, detection by an FID, and at the end, the calculation. That principle is the same for all these methods. The big difference is the type of column that you use, and that's represented in the 2 graphs below, where in the low temperature SIMDIS, you'll see a graph with a very thick stationary phase, versus on a high temperature SIMDIS used for heavier products, we only have a very thin stationary phase. That all has to do with the boiling point range of the product and the ability of the column, or the use of the column to separate the product into as much as possible, but still within the range, the boiling point range of the product. So to summarize, SIMDIS is a technique based on the same concept, components eluting boiling point order from a column, and the column is the difference for the different SIMDIS methods, and that results in a good separation. A little more about standardization. You may wonder whether SIMDIS can be used for a final product specification. If I focus on the European methods, you see that, for example, in the EN 590, the diesel specification method, it is listing the 86, or the ISO 3405, but it mentions that correlated data from SIMDIS, and they call it predicted data from SIMDIS, can be used to specify the diesel. It's not the referee method, but it's allowed to use. And we'll come later in the presentation, more details about that. And that's the same for the DEF standard for the jet fuel, the same story. It allows correlated SIMDIS data, and more about the correlation later on. How does SIMDIS compare to physical distillation? Well, physical distillation, what we mean by that is the, for example, the optidist, where we do atmospheric distillation, but that can also be micro distillation or vacuum distillation. And also another technique is the true boiling point, the 15 plates, ASTM 2892, and then of course the SIMDIS, which is true boiling point data. More about this. If we look to the 86, and this is a very old picture, of course, what you do is you fill a distillation flask with your sample, you apply heat to it, the sample starts to vaporize, raise to the neck of the flask, and then condenses through the into a metering flask. That is a one-step distillation, a one-plate distillation. So one time from liquid to gas and from gas to liquid. Thereby the separation taking place is not that accurate. And that's why they call it an average boiling point distribution. The data is less detailed because the one plate. If we go to the more average boiling point, the let's say the 15 plate, what's already in the name, there are 15 plates, so your separation is already better than on the one step, on the one plate distillation. If we start comparing, and that's already here at the bottom line, to a GC column used in SIMDIS, chromatography, the quality of columns in chromatography is often referred to in the number of theoretical plates. And there's the word plate again, and from the 15 theoretical plate system to the, let's say, the average boiling point being a one plate system, a GC column has easily far over 1,000 theoretical plates. Having said that, it means that the separation is much better, and therefore we call, and not only we, the industry calls SIMDIS the true boiling point data, because it's a very good separation taking place. One of the other differences of the TBP, true boiling point, versus the physical distillation is that you can go up to higher temperatures. We can run, as you have seen, residues or crude oil and provide data with a final boiling point up to 750 degrees C. There's a high level of automation on a GC. You can put an auto sampler on there and you can run sequences unattended overnight. Looking at the standardization methods, the reproducibility and the repeatability of SIMDIS is very good. And another argument for true boiling point for SIMDIS is the speed of analysis. Maybe not so much for high temperature SIMDIS, which can take up to 45 minutes, but jet fuel and diesel can be done in less than 10 minutes, automated, unattended. If I summarize what I've just mentioned, so the differences between, let's say, the physical distillation, the D86 compared to SIMDIS is that physical distillation reports boiling point versus volume percent. You measure the volume condensing in the metering flask, where SIMDIS reports versus mass percent, because we detect what comes out of the column by an FID. Physical distillation is an average boiling point at a given boiling point of a mixture at a given point, and SIMDIS is true boiling point. Speed of analysis was mentioned. The amount of sample used in SIMDIS is less than physical distillation. The product range, the scope of the SIMDIS is also wider than in physical distillation. And last but not least, it has a high safety standard. There's no, for a couple of reasons, there is no risk of catching fire by breaking flasks. There you work with far less samples, so there is less emission of vapors in the lab and so on. Well, so far as introduction, let's look on how we do it. How does SIMDIS work? So let's look at the hardware and software later on as well. So what do you need to do SIMDIS? You need a GC, you need an analyzer. We don't call it a GC because it's an analyzer because we deliver it as a full package. That system needs to have an inlet. We use the TPI. It needs to have a non-polar boiling point column for the separation, depending on the method, which type of column you use, and it uses a detector being the FID. And of course, not listed here is the auto sampler to introduce the sample in a repeatable way. Then you need some software to do the calculation. That's the CDS, the chromatography data system, often GAMStation or OpenLab, and whatever other packages may be around, and dedicated SIMDIS software, which takes the results and processes it accordingly. And I will give you a demo later on. Last but not least, you need to calibrate the system. I've shown you the normal paraffin mixture. You also need to check the response and the system performance by using a reference oil. There is other reference material available as listed in the methods, helping you to check whether your system performs as it should and whether it meets specifications, so to say. Well, Arjan said I will already mention this more often, but what we do, here you go. What we do as PSC, we offer a total package as a guaranteed and turnkey solution. What does that mean? That every SIMDIS analyzer we sell is tested here in our test facilities here in Rotterdam, and the system is put on the bench, the method is implemented, it's conditioned, it's calibrated, it's validated, and only when we are sure it's meeting specification, we ship the unit to you as a customer, where our certified engineers, in your case from SRA, can put the instrument on the table, check its performance, and you can start analyzing samples. As simple as that. There is no time for you to invest on looking for reference material, what column to use, what software package, etc. No, we deliver this as one total guaranteed package. Technically, the TPI, temperature programmable inlet, is a inlet we already have, I will not say for 40 years, but maybe for 38 years. This is the second generation of it, and it is designed for doing SIMDIS analysis. The sample introduced should go into the capillary column without any loss of integrity. What we mean by that, what you inject should go into the column. Small exception on that, and that is the residual parts. I will show you. Often samples are introduced direct as such. So for jet fuel and diesel, you do a direct injection. For heavier products like crude or residual samples, you need to dilute it with carbon disulfide, which when you inject, liquid will go into the gas phase, giving a large volume. So your liner in the system should be able to deal with that. Listed here a few of the features. So optimized for carbon disulfide. There's a seal leak check option on it. It's designed for high temperatures. There is no discrimination, being very important, and it has a septum purge so that there is no residuals coming in the system later on. Like I said, this is in there for many years. It's listed here 20 years. I should adjust that to 30 plus years, because when I started working for the company 30 years ago, we already had this inlet. That means that 1,000 plus SIMDISes all around the world supplied by us have this type of inlet. So it's a proven inlet. What is special about this is that you introduce your sample in a relative cool inlet. and then you start to program it, and the graph on the right hand shows the orange line, which is temperature profile of the inlet to the probe, and the blue line is the from the oven, so it's always ahead of the oven. But by doing that, you avoid that your system overloads, and you make use of the solvent effect by having this lower initial column temperature. Non-vaporized components, the residual parts, as I mentioned, are retained in the liner. I will show you a picture of that. And then there is the septum purge to eliminate memory, and that's what I also will show you. Here are some pictures of the liner that we use in our TPI. On the top you see I hope you can see, it is a clean new liner not being used. And far right bottom here you see a more graphical representation where this is the part where you inject, then the tapered bottom of it is where the column seals to it. So again, there is no splitting or whatsoever. What we have done is injected, taking a liner which has been used for quite a while for heavy products, residual products. And what you see is that residual material starts to build up over here. That's good that it builds up over here, because otherwise it would go into your column. Like with an on-column injection, this dark black brown spot will be in your column, and then not only that ½ centimeter as you see here, but the first centimeters, and that will definitely affect the separation of your components on the column. And that's the nice thing about this liner, about the TPI, is that the residuals stay in the liner and do not go into the column. This one you see the needle where it goes in, so that's exactly at that position. And here you see how the column is connected in the tapered part, and that's a leak tight connection. And here you see the brown part, exactly where the needle goes in. So the reason for using this technology is that you do not want the residual material to go into your column, because if you do that with an on-column technique, on-column inlet, you will regularly have to take the column out, cut 10-20 centimeters from it, recalibrate, and so on. And by using the TPI, it's a matter of simply replacing the liner. That's it. The septum purge. What happens when you introduce your sample? The syringe goes in, the plunger goes down, and you get a spray of the liquid in the liner, and where it evaporates, and it pulls out very quickly. There may be some droplets of the liquid on the needle, and when the needle withdraws itself from the septum, it may clean itself on the septum, and that the septum is cold, so that product may introduce in the column at a later stage. And that is what you see here on this graphs here on the mid distillate. And of course this is very much zoomed in, but here you see the results from a system without the septum purge, and here you see how nicely and clean the baseline remains. And that's the same on high temperature SIMDIS. So this is what you want, and not this, because this will affect your results. Another nice feature about our SIMDIS is that we modify the autosampler that we use for high temperature SIMDIS specifically, and we call it optimized for light solvents. You can imagine that when with high temperature SIMDIS you go to over temperatures of 430 degrees C, same for the inlet. So there is quite some heat accumulating on top of the GC, especially the point where the autosampler stands on, and that the sample is taken into the needle, and that needle is hanging above the hot area, may result in evaporation of the solvent. And what we do, we mount a little cooling fan on top which blows cool air from the top of the inlet down over the top of the DC, thereby cooling the needle and the file standing there. And what you see is the temperature profile over here, the orange one. So you see it can go above the boiling point temperature of carbon disulfide, and with the optimized autosampler it nicely stays below the boiling point. You can say, well, what does that mean? Well, that means that your repeatability on high temperature SIMDIS, where you dilute your sample with carbon disulfide, is much, much better. On the left hand is a standard autosampler, and on the right hand 10 graphs of or is it 10, whatever, number of graphs of chromatograms using the light solvent optimized autosampler. And you see that the R&D, the RSD, relative standard deviation, improves from 7% to less than 1%, which is very good, of course. Looking into the columns, so we have the autosampler for the introduction, then the TPI bringing the product into the column. The different columns I already mentioned, the difference is in the dimensions, the film thickness and the length. And here just shown typically columns used. And we always use stainless steel capillary columns, which has a much longer lifetime, especially for high temperature SIMDIS, where you go to very high oven temperatures. Then last step is the calibration and the quality control samples. I mentioned that we deliver the whole package with the instruments, and that is calibration material, that's a reference material, that are quality control samples with consensus value based on interlaboratory studies. And every SIMDIS we deliver is delivered with a set of samples that can be, and that is depending on the method implemented on the system audit. So far about methods, standardization, hardware, etc. Let's move on to correlations and crude oil distillation. But maybe, Arjan, are there already any questions in the chat, or Gianluca?
I'm checking, but maybe Laura and Gianluca can answer, so you can take a sip before that.
That's why I asked.
Yeah, not yet. Non ci sono domande. Comunque, ecco, volevo solo ricordarvi, per qualsiasi domanda potete utilizzare la sessione domande che trovate sul pannello di controllo. Tranquillamente scrivete le domande in italiano, in inglese, come volete, e noi poi le condividiamo con i colleghi. Grazie.
Okay.
Yeah.
Theo?
Continue?
Yes.
Yeah. Okay. Let's move on. It's a bit weird now to start talking about D86 reporting, because this session is about simulated distillation. But I've also shown you that for product specification, you can use SIMDIS, but then you need to use what they call predicted D86 results. And therefore we have the ability to, with our analysis, to some of them at least, to report D86 data as well. And let's have a closer look at that. Short sidestep, because this is not really simulated distillation. This is what we call detailed hydrocarbon analysis. But it's an application we have, and we call it AC8612. AC Analytical Controls, 86 stands for D86, and 1, 2, the 12 stands for group 1 and 2 in the D86, in the physical distillation method. What we do is, on a short capillary narrow bore column, we separate components into individual components. We identify and we quantify the components, and that data is used in a dedicated patented fugacity film model calculation It's a very complex calculation, but it gives you the results as you will get from D86 for group 1 and 2. And on the right hand, you'll see an example of the results, maybe a bit small, but you see the curve, of course. You see your table with the various points, recovered, evaporated. You'll find points like time to IBP, distillation rates, but also losses, recovery, residue, read vapor pressure, etc. So all the things you normally report with your D86 comes from this AC8612 analyzer. Not covered by any standard method, by the way. It's our in-house method. Another one is the AC8634. Well, you can probably already imagine that this is D86 for group 3 and 4, so for jet and diesel, and it's based on SIMDIS. We say mid-distillate SIMDIS. You do the GC analysis, you get your diesel graph like you show here, you do your typical SIMDIS calculations, and based on these SIMDIS results, we correlate these results to D86, where the AC8612 is a calculation based on a model and physical properties of individual components. This is a correlation based on standardization data, so from ASTM in this case, but it's also covered by the ISO, where a big set of samples, jet fuel and diesel, have been analyzed, and from that the correlation has been established. And that is what you see over here on the right hand side. So from SIMDIS results, we report recovered volume percent, where SIMDIS reports mass percent, versus its boiling point. And of course, you can also have your values of interest, so that's the other way around. Yeah, so that is a correlation. Summarize, AC8612 reports D86 data for group 1 and 2, and AC8634 correlates SIMDIS data to D86 based on factors as specified in standardization. Couple of ways we can offer these solutions, these analyzers, as a single channel GC, single channel analyzer, doing either one of the two, or combined in one system, and we then call it the AC Productivity Center, specifically for group 1, 2, 3, and 4. And we then say, and that has to do with the maximum oven temperature for the columns, we do not cover the full range of the mid distances, like the 2887. It can be done once or twice, or maybe a couple of times, but we try to limit it. The throughput of such a system is very high, of course, because analysis time is somewhere from 8 to 10 minutes. It's an unattended analysis, so you can run a sequence. The system is safe. You don't use solvents or whatsoever. You just fill an autosampler file, put it on the system, and you start your analysis. And that, of course, has a very low cost per sample.
Yes.
Highly automated.
I believe, Theo, we have a very nice application notes about this, and that could be shared as well with SRA.
You're ahead of me, Arjan.
I'm sorry. Yes.
Here an example of the correlation where you see two graphs, one for the jet and one for the diesel B7, so having a 7% bio component in there. The blue line is from the SIMDIS. That same sample has been analyzed with D86, and then the correlated data is shown in the orange lines. This is just an example. We regularly check this based on the various proficiency testing programs that we join. We join the one from ASTM, we join the European one, and for every analysis that we do, we check this, and we always get this very nice results. And therefore, you can imagine it allowed to use for product specification. And then this is what Arjan is referring to. We have a very nice application note explaining this technique, the correlation and the calculation in more detail. And should you have interest in it, then our friends of SRA can provide this to you. Moving on to the next topic, which is high temperature SIMDIS and crude oil. By the way, I could have talked about how gasoline SIMDIS analysis worked. I can't talk about how regular mid-distillate SIMDIS works. We are limited in time, so I've taken just a few highlights from our portfolio to show what we are capable of doing and offering to you. So we now go to the let's say the far right end of what can be done in terms of SIMDIS in boiling point range, really heavy products. And well, why would you analyze crude oil before you maybe even buy it? Here an example of two different crudes, the Alba and the Forties, where you can clearly see that the Forties has a lot more of light products, naphtha, versus the Alba, which is now for more than half very heavy, having resids. So this is probably a more costly crude, but you'll have a lot more value can get out of it. Briefly, what is high temperature SIMDIS? SIMDIS, as described before, boiling point distribution on a capillary column. But it covers a wider range. It can go up to C120, which has a boiling point of 750 degrees C. You can do crude oil on it. You can use it for a residue type of samples, but also for lube oil, etc. Further slides will focus on crude oil analysis. I showed you the picture of the liner where you could clearly see that the residual asphaltenes, for example, stays in the liner. That means that not everything is eluting. That means we cannot report up to 100%. So we do a calculation of the recovery of such a sample, and we compare the results to the found recovery. And for recovery calculation, we use an external standard, being the reference oil. For high temperature SIMDIS, very heavy products with a high final boiling point, so we use very thin film columns. We by default use the 0.17, but we can also provide the 0.09 film thickness. You need to dilute your samples. That has a couple of reasons. A very practical one, the viscosity of the sample. But another one is the column overloading because of the very thin film thickness. You simply will not get a good separation. And we typically use carbon disulfide because that is found to be the best solvent. There are some disadvantages on that, which I will show later on. And last but not least, using a high temperature SIMDIS for products with a relative small boiling point range, or very light products like naphthas, gasolines, or diesels, is not recommended or cannot be analyzed on a high temp SIMDIS. Looking at standardization, there are two methods describing the crude oil analysis. That's the ASTM D7169 and the EN 15199-3, describing how to do this. And there are some challenges in there. You see here a graph, a chromatogram from a crude oil analysis, and the challenges are marked in the blue boxes. That's the initial boiling point and the quenching from the solvent, more about that, and then how to calculate the recovery and the final boiling point if there is any. Well, back to standardization. Both methods, as mentioned before, have in the scope in the initial paragraphs stating something about using DHA, detailed hydrocarbon analysis, for the light fraction of the crude oil, thereby improving accuracy of the analysis. And that is where the AC crude oil comes into place, being two analyzers. Be aware, two analyzers, one item SIMDIS and one DHA front end or DHA combi, more can be explained later. And that is the one that is used, recommended to use for crude oil. If we go back to the picture of the first part of the crude oil, mentioned about potential issues with initial boiling point and quenching. Well, the DHA is taking care about the analysis of this fraction. So those two issues do not exist anymore when you use a DHA front end. How does that work? We, so a small sidestep from SIMDIS to DHA. We analyze the crude oil on the DHA front end according to the two methods as shown here in the graph. We introduce the sample on an inlet where only the light fraction elutes from into the capillary column, and there we then separate that light fraction, as you can see in the glass, and from the found components in the range of C1 to C9, we calculate the boiling point distribution based on its, of course, the individual boiling point components and the mass percentage of the individual components. And that boiling point graph, as shown on the right bottom, is then used to combine it with high temperature SIMDIS data. So a chromatogram from a DHA front end may look like this. So individual components from, where is my mouse? Here, from ethane or methane up to nonane. And you see all peaks being nicely identified and of course quantified. And from that we calculate the boiling point graph, where you can see the line here and the blue parts represent the parafins being here, the red parts represent the aromatics over there, etc., etc. And from that you get a curve from IBP 0.5% up to your found recovery at C9, 151 degrees C. And this is the result of an analysis using this technique. May look a bit complex, but basically what happens is that you inject your component in a inlet which is equipped with a column, a boiling point column. So instead of a regular liner, there is a liner filled with column material, and you see the carrier gas follows the blue line all the time. So your sample is introduced here, and then the gas is going in that direction. So what happens, you will get a kind of boiling point separation on this column as shown here in graph 2, step 2. The light components elute in the column, and the residual, the red part, stays on top of this liner or partly migrate into it, as you can see here. So light components are going into the column for further separation, and the heavy material is after that backflushed to vent according to step 3, where the red which migrated into the column is then in reversed flow going to vent. And at the same time your separation takes place, as I've shown you. Well, with the results from that, we have the ability in our SIMDIS software to merge, to combine the results from the DHA with the high temperature SIMDIS. And that's what you see in this slide. In the SIMDIS software, there is a little icon called DHA. When you click on it, you can load your DHA data and it automatically merges it, giving you a detailed report here, IBP data, and then the rest from there on. SIMDIS data. Graphically, you'll see here just the first 0.7, 0.6 minutes of a SIMDIS chromatogram, and everything up to the DHA merge point is coming from the DHA, and everything afterwards is coming from SIMDIS, looking like this. And the overall recovery is calculated based on the summation of both recoveries. So the orange part is coming from the DHA, therefore stepwise, more detailed, and the blue one is coming from the SIMDIS. The repeatability of such a configuration is very good, as shown in this graph, where we have done, what is it, up to 60 analysis, and you'll see the DHA front-end repeatability is excellent with RSDs for the recovery less than 1%. And also for this one, we have a nice application note or application highlight, which we can, of course, share with you. Be aware, this is based on standardization, this technology. I'm not sure if you recall one of the first slides from Arjan, told you that we pioneered on various methods. Well, this is a method pioneered, designed by us, and is now covered by global standardization. And that you merge the results from two analyses, giving you a accurate and reliable boiling point distribution for your crude oil. Two analysis, one result. If we go to the last part of my presentation, that is about software. I mentioned that you need hardware, and I mentioned that we need software. Our software package is highly automated. You start your analysis in your chromatography data system, and everything from there on will go automatically. And we call it a workflow-oriented application. But from starting analysis, you have to do yourself till final result reporting, and even export the two limbs can be executed automatically. Should you want to take more control of it and want to do it manually, then that can be done as well. The concept chromatography data system is controlling the GC, is doing the injection, is doing integration if needed, etc. And results are exported, and where our software picks it up and processes it accordingly. That can be done either in what we call a standalone configuration or fully implemented in a networked or a client-server configuration, where you have your data secured somewhere on a server, and the users in the lab or at the office desk can work with data. All kind of options available over there. Brings me to the last step and showing you a brief demo of the software.
Yeah.
While starting up on that, maybe Arjan, you can check if there are any.
I'm checking, but I don't have a good view. So it's Laura and Gianluca. Gianluca, are there any questions coming from the audience?
Not for the moment.
Yeah, I had two questions, but
see?
maybe
Okay.
we can working on that on the end. Why not? Or if you want to have there's a question correlated to the last topics you talk about. Is about the merge. So the question is about FTM D7169 method, so DHA front end and SIMDIS merge. The question is, there is today a certified reference currently available, which allows, like in the other methods, to verify property of the analytical system. So I remember this was a topic on the time I installed the instrument, DHA and SIMDIS merge.
To my knowledge, not Fabrizio. No, not that I can recall. We can make a
same.
for you,
for my knowledge too.
No, sorry about that.
Yeah, no, but it's not from you for sure. It's from the method that is not able to elevate.
It requires a lot of work, and it requires interlaboratory study and results evaluation, etc. We once looked in it, but it's a very complex thing to do and to organize. Yeah,
for sure. Okay. The two questions we can wait the end of your presentation.
Okay. Okay. Looking at the time, just a brief overview of the software. What you look at is the main screen. I will not go in details of what other methods are available, etc. But you can have multiple instruments connected to the system. Now I need to work over here. If I go to my instruments, you can see. No, I'm not online in this case. Sorry, that's not going to work. Bad demo. But you would be able to see multiple instruments over here if you have more connected. In this case, I have the middle distillate. You see the results from that. You have the option to filter results if you say I want to look to data from a specific type of product or a specific time or whatsoever. Now I've taken here as an example jet and diesel, where we see some results. If I click on a result, you get what we call a preview. There's no information over here. If I go to the other one, so you can preview your results. If I go to the first one, if I double click on it, you see it opens. And you get a lot more of information. You get, of course, your chromatogram, where you see the elution start is defined, the elution end is defined. The definition of those two is as per the method used. And from that, IBP being 0.5%, FAP being 99.5% are defined. And you see if I hover over it, you see the results. And if I click on this icon, you see the red line represents the boiling point distribution of this product. And that is what you see in the table below. You see here the points and the found boiling points. And you can do it the other way around. So boiling point versus mass. You can say I want to see it per degree or per 10 degrees, whatever. This is all user editable, and you immediately see the results. Not configured on this one, but you could maybe, I seem to recall I have it on some of the others. No, maybe this one. Yeah, you see here the results from another type of product, and I've entered a value of interest, and in this case, just as an example, 55%, and you can enter more of them. And you say, I want to see where is that in my chromatogram. That's at that point. Just show you the ease of it. Should you not agree with what the software has done as per the method, then you can say, I can simply drag and drop my endpoint. And if I do something stupid and put it somewhere over there, you'll see the results being immediately recalculated. This is not good, of course. So you have the option to do this automatically again, and then it will put it back somewhere over there. And I always forget which one to use for that. So this is the results. Here you see the retention time. If I go to boiling point, you see that it converted the x-axis in the boiling point axis, so from retention time to boiling point. Well, where does that come from? That comes from the boiling point calibration, as shown over here. And this boiling point correlation comes from the boiling point used to calculate this result. If you want to know which one, you go to details and you go to the boiling point calibrant. And if you double click on it, it will open it automatically. And you see your boiling point calibration, your carbon, normal paraffin peaks, and the calculated lines through it. Should for whatever reason something be misidentified, you'll immediately see that here graphically represented. There's a red pie over there. You can see that this is red, it's not done properly. Couple of ways of correcting it: simply drag and drop it to the right place, or go and click on the arrow and it will put it at the right place. Should you have a complete mess out of it, and like this whatsoever, we have the ability to automatically search for the components based on 3 or 4 reference peaks. Going back to the diesel, I can do it like this, or I can say which of the samples are using this sample. So that's a cross reference from sample to the calibration used for it, or the other way around. I have a calibration which samples are calculated with this. You could go back to this one. Yeah. Correlation data available over here. Different correlations. In this case, only this one is set up. You can report according HTM as the points requested by the method, or you can say I want it just every 10%. Same for the cut points, boiling point versus volume. Volume in this case, because it's correlated data. If we go here, it is mass, just as a reminder on the difference between the two. And in this way, you can, I would say, play around with your data. You can preview your results. You can export to LIMS automatically. You can save the results as an Excel file, and so on and so on. Just to give you a kind of feeling of the capabilities of the software. Just the last few things. This one is calculated with a certain blank. Should you not be happy with the blank, then you can simply take a blank. That one is already in use. If I take another blank, put it on there. Oh, it's locked. I already saved this one, so I cannot edit it anymore. Then I have to unlock. If I take this one, is that one locked? Is that one locked?
No, this one is not.
Which one?
That one is available.
This one is available. So should I want to drag another blank to it and say this one is already linked, so I take the other one, it will recalculate immediately with the other blank. Just simply drag and drop. I can spend hours on this, showing you all the other methods, etc. But as a kind of introduction, I think this for now is sufficient.
Yeah, and of course, Theo, if you have an auto sampler on the GC, you can set up a sequence with a blank, with a reference, with a calibration, samples, and the software automatically treat the sample in the proper way.
Yes, correct. Yeah. I can show you that, but that will take another 5 or 10 minutes. But it will.
Yeah.
Right. Your analysis are started from the chromatography data system. The results exported, as I've shown, and then based on the name, on the methods, etc., it will process it accordingly according to certain rules which are defined by us and can be optimized by the user. It will even import solvent and sample weight for high temperature SIMDIS, for example, and calculate it accordingly. Yeah. No. Any other questions? Otherwise, I will go back to
we
my...
have questions. Yeah. Okay. Yeah, I can wait 2 minutes. Or I have a questions from probably his producer, not custom laboratories, for example. Talking about correlation, you just introduced the word correlation in the first slides. The correlation interested on is the D1160, so under vacuum distillation. Question is, it is still valid, means valid for all the samples that comply with the IBP and FBP, for example? Or are there limitations for some type of samples that includes, I don't know, a lot of hydrocarbon groups that can deviate results or precision?
The answer is yes, and the answer is no.
Okay, nice. Yeah, yeah. I love this kind of questions. Yeah.
No, but let me explain. I explained the D86 correlation for group 3 and 4, which is based on results from an interlaboratory study from HTM. For D1160, such a thing do not exist. There is no proven correlation from HTM or whatsoever. And let me share my webcam. Yeah, and so we have a correlation in there. That's in our software. That's a very old correlation, and to be very open and frank with you, there is no how to say that accuracy behind it. It's once developed based on a certain set of samples. Data is there, can be used in between brackets without any guarantee on the results and the applicability for certain type of samples. Where D86, jet fuel diesel, is very much narrowed bracket by the standardization with proven data, etc. Such a thing for D1160 does not exist. Okay. And to say this type of sample works and this type of sample does not work is a very difficult. That's more a matter of trial and error. And last comment on that, we have the option in our software to modify optimized correlations as in there, but then you deviate from what is standard. But it may be of help.
Theo, there is a question. You know, the sample, especially nowadays, could include also components from different origin than only fossils. So bio components from vegetable origin and so on. How the SIMDIS can be used, or what could be the evolution of the SIMDIS? What is the situation of the technique in front of this kind of samples? Yeah.
Well, the technique remains the same. Yeah.
Okay.
You introduce a sample on a column which separates on boiling point. That's what the product that you introduce is made of is not so much of importance. It's a mixture of hydrocarbons at the end, and it dilutes in boiling point order. I've shown you, for example, the diesel with the 7% FAME. You clearly see nicely a peak appearing at that area, and that's taken into the calculation. There are and I forgot the number, but we're also looking into sustainable aviation fuel and other kind of products. And we are actually in the process of starting a interlaboratory study, like we have done, or we're currently doing for Reformalizer. We're also starting something for SIMDIS, and we will include some of those products. So Arjan may approach you very soon on checking the interest at your customer base, so the audience today probably, if there is an interest in participating in this interlaboratory study.
Yes.
And that will give us in half a year or in a year time a good idea on how our system performs on those products as well. We know it works fine, but you would always like to have a proof.
Okay, it sounds really interesting because the same questions we had from different customers with different words, but okay, people is it's a bit afraid about jet fuel in the future, so I want to have a step more to be ready. So nice to have a round robin with you. Okay, we will promote in every customer location.
So as PAC, as AC Analytical Controls, we develop carotene analyzers, as mentioned multiple times. We follow what is happening in the market in terms of adapting, modifying, optimizing, checking performance of our analyzers. Just look, for example, at the reformalizer, which was a Piona in the past, and then we had the analysis of oxygenates, and we have a few years ago performed an interlaboratory study by which results we improved the scope of the method. There's one going on right now. Samples are out. We are doing that on SIMDIS as well. So we try to support our customer base and future customers in this kind of work. So it's not only delivering an instrument, but also helping you in performing the analysis and getting reliable results and having trust in the results.
I believe trust is a very good word, and I think that's also very meaningful to our end users, the customers who are now listening into it. Don't be afraid. For sure, AC Analytical Controls will make sure that we dive into these new applications. As Theo already said, from a technical point of view, it is no issue to go into that, but we want to prove that as well with an interlaboratory study, which helps you drive your business forward as well. So don't be afraid. We are here to support you.
Yeah. Thanks, Arjan.
Thank you.
Good words. Yeah. Really.
Thank you.
Oh, my Q&A list is empty now. Yeah.
Ok, se non ci sono domande penso possiamo concludere. Direi estremamente interessante il webinar di oggi. I want to thank Theo and Arjan. Your presentation really, I believe the audience appreciate really the completeness of your presentation and your knowledge, and I believe that also the number of analyzers we installed really starting from the first years of 2000 up to now is really important in Italy. So I believe that all the customers, all the audience appreciate the high value of the PAC products. Niente, noi ringraziamo tutti voi che avete partecipato a questo webinar.
Grazie a tutti.
Vedete nella slide ci sono i nostri contatti. Come diceva Theo ed Arjan, le tecniche, diciamo i nuovi campioni potranno essere sfidanti anche dal punto di vista analitico in futuro, ma proprio per questo noi con PAC siamo al vostro fianco per aiutarvi nell'affrontare le sfide analitiche che di volta in volta dovrete incontrare in futuro. Così come SRA, anche PAC è disponibile a sviluppare applicazioni custom, quindi c'è un laboratorio estremamente attrezzato anche in Olanda, in PAC, dove è possibile fare delle messe a punto e fare delle configurazioni strumentali ad hoc per applicazioni anche magari nuove, sfidanti. Di nuovo vi ringrazio per la vostra attenzione, i nostri contatti li vedete a video e alla prossima sessione. Grazie e buona giornata.
Mille
grazie a tutti. Bye bye Arjan e Theo.
Grazie, ciao ciao.
Bye bye, ciao ciao, grazie Theo, grazie Arjan.